Impulse is the product of the force applied to an object times the time that that force is applied, and that causes a change in momentum of the object. So the formula is J is equal to force times time. J is the symbol we use for impulse. So J is equal to the change in momentum. That's how we define it. And if we replace this, we get force times time is equal to the change in momentum. Now, what are we really changing when we change momentum? Well, we're changing the velocity. We wouldn't be changing the mass because then it's a different mass. So the final version of the formula is force times time is equal to the mass of the object times the change in its velocity. So here's another view. We can look at impulse, the force times time, is required to change the velocity of an object. Well, we already know that. Force times time is equal to mass times the change in velocity. If we change the velocity quickly, that means with a little bit of time, a large force is required. And we see that if we take this formula and rearrange it, F is equal to m delta v divided by t. And if we change the velocity slowly, a smaller force is required. So don't be misled. If you change the velocity quickly or slowly, it's the same impulse. Same impulse. This is a very key idea. So example, suppose a 2 kilogram object goes from 3 to 7 meters per second. So that means that delta V is 7 minus 3 or 4 meters per second. So that's our delta V. How do we accomplish that delta V? That's the question. So delta P is m delta V, or the change in momentum works out to be 8 kilogram meters per second. So keep that in mind. The change in momentum in this case is 8 meters per second. How do we accomplish that? Quickly or slowly? Well, if we do it slow, that's large time, compared to fast, which would be a small time. So if we do it slowly in 4 seconds, that means the time is very large, which means the force has to be very small, and it calculates to 2 newtons. If the time is small, that means the force is very large compared to the small time, and that works out to a force of 8 newtons. So basically what we see is that if you have the time which is smaller, we're going to end up having 8, this should read 4 times the force necessary to do it in 1/4 of the time. So both cause an identical result of 4 meters per second, or both result in a change in momentum of 8 kilogram meters per second. So what's the consequence? A fast delta V requires a large force. So the object undergoing delta V can break. That's what we're looking at. So a whole bunch of examples here. The cushion used to protect the fall of a pole vaulter or a high jumper. A car airbag. You're traveling 60 miles an hour in a car. Well, the car hits a brick wall. It goes from 60 to 0 like that really quickly. But you go 60 miles an hour to 0 very slowly as you push into the airbag. So both the car and you stop. The car stops very quickly, and you take a long time to stop, relatively long. So there's less force acting on your body. The soles of your jogging shoes. So imagine if you're jogging on hard pavement and you're pounding against that cement. Well, if you put a layer of cushion between your feet and the ground, either way your foot is going to stop when it hits the pavement, but it's how it stops that makes a difference. There's less force acting on the bottom of your feet, which means there's less force acting on your joints. A baseball glove. Imagine catching a baseball. If you're the catcher and you're catching a baseball head on, it just hits your hand like that. Or you have a layer of padding in front of your hand. What happens is the fast moving ball, maybe 100 miles an hour, hits the glove, and then it slows down to 0, which means that instead of stopping in that small little distance of your skin being compressed, what ends up happening is it goes through that distance as the cushion in the glove is compressed. It takes more time to do that, More time means less force. And helmets, your bicycle helmet, a football helmet, any kind of a helmet, the whole purpose of that is when you collide with something, either way you're going to collide. And either way you're going to go from a high speed to a low speed or no speed, zero. Well, how long is that collision going to take? If you can prolong the collision, there's less force acting on the object.